This is number 3 off of the Riemann Sums FRQ practice worksheet. We have a table of values here. We have time in terms of minutes, and at these specific times we're told how fast in terms of velocity that Joanna is jogging. So Joanna jogs along a straight path between 0 and 40 minutes. Joanna's velocity is given by the differentiable function v. Okay, so differentiable function, part of a smooth curve. Select the graphs of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. Use the data in the table to estimate the value of v prime of 16. So v prime of 16 is asking for the acceleration rate of change of Joanna, of the rate of change of velocity. So what we can do is we can do change in velocity over change in time. So 240 minus 200 over 20 minus 12. So that gives us 5 meters per minute squared. Okay. And this is just an approximation. We don't know the exact acceleration at 16 minutes. The best we can do is choose the two closest order pairs and do slope. For part B, using correct units, explain the meaning of the definite integral 0 to 40, absolute value of v of t. Approximate the value of the definite integral from 0 to 40 of the absolute value of v of t using a right Riemann sum with 4 subintervals indicated in the table. So we know that the definite integral from 0 to 40 of velocity is just displacement, but the integral from 0 to 40 of the absolute value of v of t is going to be the total distance. That means even if Joanna is jogging backwards, we're going to count that as a positive distance. Okay, so the total distance that Joanna jogs in the time interval from 0 to 40 is what is represented in this expression. It says approximate the value of definite integral from 0 to 40 of the absolute value of v of t using a right Riemann sum with four subintervals indicated in the table. So we're going to use right Riemann sums. So we want to we can identify the width by subtracting the time value. So 12 minus 0 is 12. 20 minus 12 is 8, 24 minus 20 is 4, 40 minus 24 is 16. And then with each subinterval, we want to choose the right endpoint. So 12 times 200 will be the first rectangle. Second rectangle has a width of 8 and the height of 240. Third rectangle has a width of 4 and a height of negative 220, but because it's absolute value, we want to count that as a positive velocity, so it'll be 4 times 220. And then the last interval has a width of 16 and a height of 150. We add those rectangles together, we total those areas, and we get 7,600 meters. On the AP exam, you can leave your answer unsimplified, especially if it's non-calculator portion. We want to make sure we do that. For part C, Bob is riding his bicycle along the path. For t between 0 and 10, Bob's velocity is modeled by b of t. So this is the velocity function, where t is measured in minutes and b of t is measured in meters per minute. Find the acceleration at time t equals 5. Well, if b of t is the velocity function, then acceleration is the derivative of this velocity function. So b prime is going to be 3t squared minus 12t. And if we want to find the acceleration at t equals 5, we can plug 5 into the acceleration function. We get 3 times 5 squared minus 12 times 5, and this gives us 15 meters per minute squared. We're dealing with acceleration, okay. So our units of measure have to match. For part D, based on the model from part B, based on the model B from part C, find Bob's average velocity. So average velocity is average value theorem, 1 over b minus a, integral from a to b of v of t dt. Our a and b values are 0 and 10. That's our starting time and our ending time. And then we do definite integral from 0 to 10 of the integral of velocity. So this will bring us up to, this will find, but we have to do this by hand. This is non-calculator portion, so we got to go through power rule. So power rule t to the 4th over 4, 6t cubed over 3, 300t. Now we can plug in the upper and lower bound. Make sure that you don't plug the 10 and 0 into the integrand. You got to take the time to find the antiderivative first. So once I find the antiderivative, I'm going to plug in the 10 and 0. The 10 gets plugged in for all the t's first, minus, then I plug in all the zeros. Careful, when you plug in the zeros, most of the time it does zero out all the terms, but sometimes it doesn't. In this case it does, but just be careful, especially if you're plugging a variable into the exponent, or if you're dealing with natural logs or different variations. Just be careful with zeros. Not all the time are we going to be guaranteed that 0 will just wipe everything out. So after I evaluate, I still have that 1/10 out in front, so I multiply the 1/10 through, and I'm going to leave my answer in unsimplified form. Average velocity, so my units have to match what we know of velocity, so meters per minute. So leave your answer in this form, even though we could simplify it down to 350 meters per minute. But this is the safer way to go, especially if it's non-calculator FRQ portion where we want to be able to move forward as soon as we have a version of the correct answer.